Welcome to This Explainer. Today, we're taking a seriously mind-bending journey through the sheer physical scale of computing history. If you've ever wondered how the tech that basically dictates our modern lives evolved from massive iron gears to invisible artificial intelligence, well, you're in the right place. Let's just dive right in.
Okay, so did you know the first computers were actually meant to run on steam power? I know, it sounds totally like science fiction, maybe something straight out of a steampunk novel, but it's absolutely true. When we think of computers today, our brains instantly jump to electricity, right? Batteries, silicon chips, but we need to completely shatter that mental model for a second. Back in 1837, this brilliant inventor named Charles Babbage designed what he called the analytical engine. And since commercial electricity just wasn't a reality yet, his design was 100% mechanical. We're talking about a massive machine made of interlocking iron gears, levers, and brass. And the proposed power source to make this whole thing calculate? Steam power. It's just wild to realize that the conceptual blueprint for a computer literally started in the era of steam locomotives.
Now, let's jump forward about a century to when electricity did become the standard. 27. What does that number represent? Is it the memory size, processing speed? No way. That is the weight, in tons, of the ENIAC computer, which was completed around 1940. 27 tons. To put that into perspective, that's roughly the weight of 4 full-sized elephants combined just to do some basic calculations. So we went from the theoretical steam engine of Babbage to a very real, very electrical behemoth. It really emphasizes the extreme, clunky, physical beginnings of the digital age.
Let's flesh out the reality of this 27-ton machine for a second. The ENIAC didn't just sit on a desk. It was the desk, the walls, and the entire room. It required 1,800 square feet just to exist. Imagine a whole modern multi-bedroom house dedicated entirely to one single machine. And to make it function, it housed 18,000 vacuum tubes. Operating this beast wasn't a matter of typing on a keyboard. It actually required physically walking through the aisles of this massive space, totally surrounded by thousands of fragile, glowing glass tubes that threw off intense heat. It was heavy, it was incredibly slow, and it was literally physical labor just to run a simple program.
Let's move to the timeline and see how this all builds. We've got our mechanical start in 1837 with the analytical engine, and then we jump over 100 years to 1940, where electricity brings us the massive ENIAC. But notice how the gaps between these milestones start getting smaller. The timeline is compressing. The evolution of this tech starts shifting from a slow crawl to a rapid exponential sprint over just a little more than a century. And that brings us to a highly specific, kind of hilarious moment in 1947 that forever changed how we talk about technology.
Section 1. The first computer bug. We use this piece of technical jargon literally every single day. If our app crashes or our smartphone freezes up, we just say it has a bug. But back in 1947, renowned computer scientist Grace Hopper was working on a massive room-sized computer, a lot like the ones we were just talking about, filled with thousands of glowing vacuum tubes. Suddenly, the machine just halted, stopped dead. When her team physically inspected the hardware, they found the culprit. And it wasn't a mathematical error. It was a literal frantic moth that had flown into the machine, gotten trapped inside one of those hot vacuum tubes, and died. An actual insect brought a multi-million-dollar calculating machine to its knees.
And get this, they actually removed the dead moth with tweezers and taped it directly into their engineering logbook with this exact note written right next to it. First actual case of bug being found. This literal log entry forever cemented the word bug into our modern digital vocabulary. So every time a software engineer complains about debugging code today, they are tracing a direct linguistic lineage back to a dead moth in 1947. It perfectly captures how deeply physical early computing really was.
Section 2. The Silicon Revolution.
Now, by the 1970s, the computing world turns completely upside down. The physical reality of those massive machines is totally shattered. And this brilliantly illustrates the shift. On one side, we have that 1940s reality, an 1,800 square foot room just to house a single machine. But on the other side, the 1970s reality, the microprocessor, a piece of silicon literally the size of your fingertip. In just 30 years, engineers managed to shrink a room's worth of processing power, all those glass tubes, all the wires, all that intense heat, down onto a microscopic silicon chip that you could balance on the tip of your index finger. It is arguably the greatest leap in miniaturization in human history.
And because of that tiny little chip, absolutely everything changed. This specific leap in miniaturization is what allowed visionary companies like Apple and Microsoft to do the unthinkable. They took computers out of the domain of massive government and university labs and put them right inside normal people's homes. The personal computer was born. And from there, well, the trajectory was set. That same shrinking process just kept continuing, year after year, eventually evolving into the highly advanced smart technology we casually carry around in our pockets every single day.
Section 3. The future, quantum, and AI.
We are now living in an era that Charles Babbage, even with all his visionary brilliance, couldn't have possibly dreamed of back in 1837. We've moved way beyond silicon chips and into the mind-bending realms of quantum computing and artificial intelligence. The absolutely crucial point here is the sheer speed of this new era. Look at this contrast. If you give a standard, highly advanced modern computer a tremendously complex mathematical problem, it might take it literally thousands of years to compute the final answer. But a quantum computer, utilizing the very principles of quantum mechanics, it can solve that exact same equation in a few seconds. A few seconds! The processing power is so vast, so incredibly mind-blowing, that it effectively breaks the rules of traditional computing speed. It's a leap just as big as going from those mechanical iron gears to silicon.
But it's not just about raw speed. It's about how these machines actually operate. Artificial intelligence has totally shifted machines from being mere calculators, devices that just crunch numbers when we tell them to, into autonomous entities. We're now dealing with digital systems that can recognize complex patterns, solve dynamic problems, and even create original art, text, and solutions entirely independently. They're starting to think and create in ways that really mimic human cognition. The computer is no longer just a static tool, it's practically becoming a collaborator. So, stepping back for a second to look at this grand narrative arc of scale and speed we've explored today, we started with massive iron gears and steam in the 1800s. Then, we transitioned to those giant rooms filled with heat, wires, and fragile glass vacuum tubes in the 1940s. And finally, through the Silicon Revolution, the computer became smaller, faster, and infinitely more powerful until it transformed into the almost invisible, ubiquitous digital brain that basically orchestrates our entire modern world today. It went from a clunky 27-ton giant to a microscopic powerhouse. Which naturally brings us to the ultimate question. If we've gone from steam-powered gears to thinking artificial intelligence in less than 2 centuries, where in the world is computing heading next?